Systems have been developed to create transgenic organisms in a wide variety of other animals. Chickens have been genetically modified for a variety of purposes. This includes studying embryo development, 284 preventing the transmission of bird flu, 285 and providing evolutionary insights using reverse engineering to recreate dinosaur-like phenotypes. 286 a GM chicken that produces the drug Kanuma, an enzyme that treats a rare condition, in its egg passed U.S. regulatory approval in 2015. 287 genetically modified frogs, in particular Xenopus laevis and Xenopus tropicalis, are used in developmental biology research. GM frogs can also be used as pollution sensors, especially for endocrine-disrupting chemicals. 288 there are proposals to use genetic engineering to control cane toads in Australia. 290 the nematode Caenorhabditis elegans is one of the major model organisms for researching molecular biology. 291 RNA interference RNAi was discovered in C. elegans. 292 and could be induced by simply feeding them bacteria modified to express double-stranded RNA. 293 it is also relatively easy to produce stable transgenic nematodes, and this along with RNAi are the major tools used in studying their genes. 294 the most common use of transgenic nematodes has been studying gene expression and localization by attaching reporter genes. Transgenes can also be combined with RNAi techniques to rescue phenotypes, study gene function, image cell development in real time, or control expression for different tissues or developmental stages. 294 transgenic nematodes have been used to study viruses, 295 toxicology, 296 diseases, 297, 298 and to detect environmental pollutants. 299 transgenic hydra expressing green fluorescent protein. The gene responsible for albinism in sea cucumbers has been found and used to engineer white sea cucumbers, a rare delicacy. The technology also opens the way to investigate the genes responsible for some of the cucumber's more unusual traits, including hibernating in summer, eviscerating their intestines, and dissolving their bodies upon death. 300 flatworms have the ability to regenerate themselves from a single cell. 301 until 2017 there was no effective way to transform them, which hampered research. By using microinjection and radiation, scientists have now created the first genetically modified flatworms. 302 the bristleworm, a marine annelid, has been modified. It is of interest due to its reproductive cycle being synchronized with lunar phases, regeneration capacity and slow evolution rate. 303 Cnidaria such as Hydra and the sea anemone Nematostella vectensis are attractive model organisms to study the evolution of immunity and certain developmental processes. 304 other animals that have been genetically modified include snails, 305 geckos, turtles, 306 crayfish, oysters, shrimp, clams, abalone, 307 and sponges. 308 regulation. Genetically modified organisms are regulated by government agencies. This applies to research as well as the release of genetically modified organisms, including crops and food. The development of a regulatory framework concerning genetic engineering began in 1975, at Asilomar, California. The Asilomar meeting recommended a set of guidelines regarding the cautious use of recombinant technology and any products resulting from that technology. 309 The Cartagena Protocol on Biosafety was adopted on the 29th of January 2000 and entered into force on the 11th of September 2003. 310 It is an international treaty that governs the transfer, handling, and use of genetically modified organisms. 311 157 countries are members of the protocol and many use it as a reference point for their own regulations. 312 Universities and research institutes generally have a special committee that is responsible for approving any experiments that involve genetic engineering. Many experiments also need permission from a national regulatory group or legislation. All staff must be trained in the use of GMOs and all laboratories must gain approval from the regulatory agency to work with GMOs. 313 The legislation covering GMOs are often derived from regulations and guidelines in place for the non-GMO version of the organism, although they are more severe. 314 There is a near-universal system for assessing the relative risks associated with GMOs and other agents to laboratory staff and the community. They are assigned to one of 4 risk categories based on their virulence, the severity of the disease, the mode of transmission, and the availability of preventive measures or treatments. There are 4 biosafety levels that a laboratory can fall into, ranging from level 1, which is suitable for working with agents not associated with disease, to level 4, working with life-threatening agents. Different countries use different nomenclature to describe the levels and can have different requirements for what can be done at each level. 314 A label marking this peanut butter as being non-GMO. Detail of a French cheese box declaring, GMO-free. Production, i.e., below 0.9%. There are differences in the regulation for the release of GMOs between countries, with some of the most marked differences occurring between the US and Europe. 315 Regulation varies in a given country depending on the intended use of the products of the genetic engineering. For example, a crop not intended for food use is generally not reviewed by authorities responsible for food safety. 316 Some nations have banned the release of GMOs or restricted their use, and others permit them with widely differing degrees of regulation. 317, 318, 319, 320 In 2016, 38 countries officially ban or prohibit the cultivation of GMOs and 9 Algeria, Bhutan, Kenya, Kyrgyzstan, Madagascar, Peru, Russia, Venezuela and Zimbabwe ban their importation. 321 Most countries that do not allow GMO cultivation do permit research using GMOs. 322 Despite regulation, illegal releases have sometimes occurred, due to weakness of enforcement. 8. The European Union (EU) differentiates between approval for cultivation within the EU and approval for import and processing. 323. While only a few GMOs have been approved for cultivation in the EU, a number of GMOs have been approved for import and processing. 324. The cultivation of GMOs has triggered a debate about the market for GMOs in Europe. 325. Depending on the coexistence regulations, incentives for cultivation of GM crops differ. 326. The U.S. policy does not focus on the process as much as other countries, looks at verifiable scientific risks and uses the concept of substantial equivalence. 327. Whether gene-edited organisms should be regulated the same as genetically modified organism is debated. USA regulation sees them as separate and does not regulate them under the same conditions, while in Europe a GMO is any organism created using genetic engineering techniques. 28. One of the key issues concerning regulators is whether GM products should be labeled. The European Commission says that mandatory labeling and traceability are needed to allow for informed choice, avoid potential false advertising, 328, and facilitate the withdrawal of products if adverse effects on health or the environment are discovered. 329. The American Medical Association, 330, and the American Association for the Advancement of Science, 331, say that absent scientific evidence of harm even voluntary labeling is misleading and will falsely alarm consumers. Labeling of GMO products in the marketplace is required in 64 countries. 332. Labeling can be mandatory up to a threshold GM content level, which varies between countries, or voluntary. In the U.S., the National Bioengineered Food Disclosure Standard, mandatory compliance date, January 1, 2022, requires labeling GM foods. 333. In Canada, labeling of GM food is voluntary. 334. While in Europe all food, including processed food, or feed which contains greater than 0.9% of approved GMOs must be labeled. 335. In 2014, sales of products that had been labeled as non-GMO grew 30% to $1.1 billion. 336. Controversy. There is controversy over GMOs, especially with regard to their release outside laboratory environments. The dispute involves consumers, producers, biotechnology companies, governmental regulators, non-governmental organizations, and scientists. Many of these concerns involve GM crops and whether food produced from them is safe and what impact growing them will have on the environment. These controversies have led to litigation, international trade disputes, and protests, and to restrictive regulation of commercial products in some countries. 337. Most concerns are around the health and environmental effects of GMOs. These include whether they may provoke an allergic reaction, whether the transgenes could transfer to human cells, and whether genes not approved for human consumption could outcross into the food supply. 338. A protester advocating for the labeling of GMOs. There is a scientific consensus, 339, 340, 341, 342, that currently available food derived from GM crops poses no greater risk to human health than conventional food, 343, 344, 345, 346, 347, but that each GM food needs to be tested on a case-by-case basis before introduction. 348, 349, 350. Nonetheless, members of the public are much less likely than scientists to perceive GM foods as safe. 351, 352, 353, 354. The legal and regulatory status of GM foods varies by country, with some nations banning or restricting them, and others permitting them with widely differing degrees of regulation. 355, 356, 357, 358. As late as the 1990s, gene flow into wild populations was thought to be unlikely and rare, and if it were to occur, easily eradicated. It was thought that this would add no additional environmental costs or risks. No effects were expected other than those already caused by pesticide applications. 359. However, in the decades since, several such examples have been observed. Gene flow between GM crops and compatible plants, along with increased use of broad-spectrum herbicides, 360, can increase the risk of herbicide-resistant weed populations. 361. Debate over the extent and consequences of gene flow intensified in 2001 when a paper was published showing transgenes had been found in La Raza maize in Mexico, the crop's center of diversity. 362. 363. Gene flow from GM crops to other organisms has been found to generally be lower than what would occur naturally. 364. In order to address some of these concerns, some GMOs have been developed with traits to help control their spread. To prevent the genetically modified salmon inadvertently breeding with wild salmon, all the fish raised for food are females, triploid, 99% are reproductively sterile, and raised in areas where escaped salmon could not survive. 365. 366. Bacteria have also been modified to depend on nutrients that cannot be found in nature. 367. And genetic use restriction technology has been developed, though not yet marketed, that causes the second generation of GM plants to be sterile. 368. Other environmental and agronomic concerns include a decrease in biodiversity, an increase in secondary pests, non-targeted pests, and evolution of resistant insect pests. 369, 370, 371. In the areas of China and the U.S. with Bt crops, the overall biodiversity of insects has increased and the impact of secondary pests has been minimal. 372. Resistance was found to be slow to evolve when best practice strategies were followed. 372. The impact of Bt crops on beneficial non-target organisms became a public issue after a 1999 paper suggested they could be toxic to monarch butterflies. Follow-up studies have since shown that the toxicity levels encountered in the field were not high enough to harm the larva. 373. Accusations that scientists are playing God and other religious issues have been ascribed to the technology from the beginning. 374. With the ability to genetically engineer humans now possible, there are ethical concerns over how far this technology should go, or if it should be used at all. 375 Much debate revolves around where the line between treatment and enhancement is and whether the modifications should be inheritable. 376 Other concerns include contamination of the non-genetically modified food supply. 378 The rigor of the regulatory process. 380 Consolidation of control of the food supply in companies that make and sell GMOs. 381 Exaggeration of the benefits of genetic modification. 382 Are concerns over the use of herbicides with glyphosate. 383 Other issues raised include the patenting of life. 384 And the use of intellectual property rights. 385 There are large differences in consumer acceptance of GMOs, with Europeans more likely to view GM food negatively than North Americans. 386 GMOs arrived on the scene as the public confidence in food safety, attributed to recent food scares such as bovine spongiform encephalopathy and other scandals involving government regulation of products in Europe, was low. 387 This along with campaigns run by various non-governmental organizations, have been very successful in blocking or limiting the use of GM crops. 388 NGOs like the Organic Consumers Association, the Union of Concerned Scientists, 389 390, 391 Greenpeace and other groups have said that risks have not been adequately identified and managed, 392, and that there are unanswered questions regarding the potential long-term impact on human health from food derived from GMOs. They propose mandatory labeling, 393, 394, or a moratorium on such products. Climate change. Present-day climate change includes both global warming, the ongoing increase in global average temperature, and its wider effects on Earth's climate. Climate change in a broader sense also includes previous long-term changes to Earth's climate. The current rise in global temperatures is driven by human activities, especially fossil fuel burning since the Industrial Revolution. 3. Fossil fuel use, deforestation, and some agricultural and industrial practices release greenhouse gases. 5. These gases absorb some of the heat that the Earth radiates after it warms from sunlight, warming the lower atmosphere. Carbon dioxide, the primary greenhouse gas driving global warming, has grown by about 50% and is at levels not seen for millions of years. 6. Changes in surface air temperature over the past 50 years. 1. The Arctic has warmed the most, and temperatures on land have generally increased more than sea surface temperatures. Earth's average surface air temperature has increased almost 1.5 degrees Celsius, about 2.5 degrees Fahrenheit, since the Industrial Revolution. Natural forces cause some variability, but the 20-year average shows the progressive influence of human activity. 2. Climate change has an increasingly large impact on the environment. Deserts are expanding, while heat waves and wildfires are becoming more common. 7. Amplified warming in the Arctic has contributed to thawing permafrost, retreat of glaciers and sea ice decline. 8. Higher temperatures are also causing more intense storms, droughts, and other weather extremes. 9. Rapid environmental change in mountains, coral reefs, and the Arctic is forcing many species to relocate or become extinct. 10. Even if efforts to minimize future warming are successful, some effects will continue for centuries. These include ocean heating, ocean acidification and sea level rise. 11. Climate change threatens people with increased flooding, extreme heat, increased food and water scarcity, more disease, and economic loss. Human migration and conflict can also be a result. 12. The World Health Organization calls climate change one of the biggest threats to global health in the 21st century. 13. Societies and ecosystems will experience more severe risks without action to limit warming. 14. Adapting to climate change through efforts like flood control measures or drought-resistant crops partially reduces climate change risks, although some limits to adaptation have already been reached. 15. Poorer communities are responsible for a small share of global emissions, yet have the least ability to adapt and are most vulnerable to climate change. 16. 17. Examples of some effects of climate change: wildfire intensified by heat and drought, bleaching of corals occurring more often due to marine heatwaves, and worsening droughts compromising water supplies. Many climate change impacts have been observed in the first decades of the 21st century, with 2023 the warmest on record at plus 1.48 degrees Celsius, 2.66 degrees Fahrenheit, since regular tracking began in 1850. 1920 Additional warming will increase these impacts and can trigger tipping points, such as melting all of the Greenland ice sheet. 21 Under the 2015 Paris Agreement, nations collectively agreed to keep warming well under 2 degrees Celsius. However, with pledges made under the agreement, global warming would still reach about 2.8 degrees Celsius, 5.0 degrees Fahrenheit, by the end of the century. 22 Limiting warming to 1.5 degrees Celsius would require having emissions by 2030 and achieving net zero emissions by 2050. 24 Fossil fuel use can be phased out by conserving energy and switching to energy sources that do not produce significant carbon pollution. These energy sources include wind, solar, hydro, and nuclear power. 25 Cleanly generated electricity can replace fossil fuels for powering transportation, heating buildings, and running industrial processes. 26 Carbon can also be removed from the atmosphere, for instance by increasing forest cover and farming with methods that capture carbon in soil. 27 Terminology. Before the 1980s it was unclear whether the warming effect of increased greenhouse gases was stronger than the cooling effect of airborne particulates in air pollution. Scientists use the term inadvertent climate modification to refer to human impacts on the climate at this time. 28 In the 1980s, the terms global warming and climate change became more common, often being used interchangeably. 29 30 31 Scientifically, global warming refers only to increased surface warming, while climate change describes both global warming and its effects on Earth's climate system, such as precipitation changes. 28 Climate change can also be used more broadly to include changes to the climate that have happened throughout Earth's history. 32. Global warming, used as early as 1975. 33. Became the more popular term after NASA climate scientist James Hansen used it in his 1988 testimony in the U.S. Senate. 34. Since the 2000s, climate change has increased usage. 35. Various scientists, politicians and media may use the terms climate crisis or climate emergency to talk about climate change, and may use the term global heating instead of global warming. 36. 37. Global temperature rise. Temperatures prior to present-day global warming. Global surface temperature reconstruction over the last 2,000 years using proxy data from tree rings, corals, and ice cores in blue. 38. Directly observed data is in red. 39. Over the last few million years the climate cycled through ice ages. One of the hotter periods was the last interglacial, around 125,000 years ago, where temperatures were between 0.5 degrees Celsius and 1.5 degrees Celsius warmer than before the start of global warming. 40. This period saw sea levels 5 to 10 meters higher than today. The most recent glacial maximum 20,000 years ago was some 5 to 7 degrees C colder. This period has sea levels that were over 125 meters, 410 feet lower than today. 41. Temperatures stabilized in the current interglacial period beginning 11,700 years ago. 42. This period also saw the start of agriculture. 43. Historical patterns of warming and cooling, like the medieval warm period and the Little Ice Age, did not occur at the same time across different regions. Temperatures may have reached as high as those of the late 20th century in a limited set of regions. 44. 45. Climate information for that period comes from climate proxies, such as trees and ice cores. 46. 47. Warming since the Industrial Revolution. In recent decades, new high temperature records have substantially outpaced new low temperature records on a growing portion of Earth's surface. 48. There has been an increase in ocean heat content during recent decades as the oceans absorb over 90% of the heat from global warming. 49. Around 1850 thermometer records began to provide global coverage. 50. Between the 18th century and 1970 there was little net warming, as the warming impact of greenhouse gas emissions was offset by cooling from sulfur dioxide emissions. Sulfur dioxide causes acid rain, but it also produces sulfate aerosols in the atmosphere, which reflect sunlight and cause global dimming. After 1970, the increasing accumulation of greenhouse gases and controls on sulfur pollution led to a marked increase in temperature. 51, 52, 53. NASA animation portraying global surface temperature changes from 1880 to 2023. The color blue denotes cooler temperatures and red denotes warmer temperatures. Ongoing changes in climate have had no precedent for several thousand years. 54. Multiple independent datasets all show worldwide increases in surface temperature. 55. At a rate of around 0.2 degrees Celsius per decade. 56. The 2014-2023 decade warmed to an average 1.19 degrees Celsius, 1.06-1.30 degrees Celsius compared to the pre-industrial baseline 1850-1900. 57. Not every single year was warmer than the last. Internal climate variability processes can make any year 0.2 degrees Celsius warmer or colder than the average. 58. From 1998 to 2013, negative phases of two such processes, Pacific Decadal Oscillation (PDO) 59 and Atlantic Multidecadal Oscillation (AMO) 60, caused a short, slower period of warming called the global warming hiatus. 61. After the hiatus, the opposite occurred, with years like 2023 exhibiting temperatures well above even the recent average. 62. This is why the temperature change is defined in terms of a 20-year average, which reduces the noise of hot and cold years and decadal climate patterns, and detects the long-term signal. 63. 5. 64. A wide range of other observations reinforce the evidence of warming. 65. 66. The upper atmosphere is cooling, because greenhouse gases are trapping heat near the Earth's surface, and so less heat is radiating into space. 67. Warming reduces average snow cover and forces the retreat of glaciers. At the same time, warming also causes greater evaporation from the oceans, leading to more atmospheric humidity, more and heavier precipitation. 68. 69. Plants are flowering earlier in spring, and thousands of animal species have been permanently moving to cooler areas. 70. Differences by region. Different regions of the world warm at different rates. The pattern is independent of where greenhouse gases are emitted, because the gases persist long enough to diffuse across the planet. Since the pre-industrial period, the average surface temperature over land regions has increased almost twice as fast as the global average surface temperature. 71. This is because oceans lose more heat by evaporation and oceans can store a lot of heat. 72. The thermal energy in the global climate system has grown with only brief pauses since at least 1970, and over 90% of this extra energy has been stored in the ocean. 73. 74. The rest has heated the atmosphere, melted ice, and warmed the continents. 75. The Northern Hemisphere and the North Pole have warmed much faster than the South Pole and Southern Hemisphere. The Northern Hemisphere not only has much more land, but also more seasonal snow cover and sea ice. As these surfaces flip from reflecting a lot of light to being dark after the ice has melted, they start absorbing more heat. 76. Local black carbon deposits on snow and ice also contribute to Arctic warming. 77. Arctic surface temperatures are increasing between 3 and 4 times faster than in the rest of the world. 78. 79. 80. Melting of ice sheets near the poles weakens both the Atlantic and the Antarctic limb of thermohaline circulation, which further changes the distribution of heat and precipitation around the globe. 81. 82. 83. 84. Future global temperatures. CMIP 6 multi-model projections of global surface temperature changes for the year 2090 relative to the 1850-1900 average. The current trajectory for warming by the end of the century is roughly halfway between these two extremes. 22, 85, 86. The World Meteorological Organization estimates there is an 80% chance that global temperatures will exceed 1.5 degrees Celsius warming for at least 1 year between 2024 and 2028. The chance of the 5-year average being above 1.5 degrees Celsius is almost half. 87. The IPCC expects the 20-year average global temperature to exceed plus 1.5 degrees Celsius in the early 2030s. 88. The IPCC Sixth Assessment Report 2021 included projections that by 2100 global warming is very likely to reach 1.0-1.8 degrees Celsius under a scenario with very low emissions of greenhouse gases, 2.1-3.5 degrees Celsius under an intermediate emission scenario, or 3.3-5.7 degrees Celsius under a very high emission scenario. 89. The warming will continue past 2100 in the intermediate and high emission scenarios. 90. 91. With future projections of global surface temperatures by year 2300 being similar to millions of years ago. 92. The remaining carbon budget for staying beneath certain temperature increases is determined by modeling the carbon cycle and climate sensitivity to greenhouse gases. 93. According to UNEP, global warming can be kept below 1.5 degrees Celsius with a 50% chance if emissions after 2023 do not exceed 200 gigatons of CO2. This corresponds to around 4 years of current emissions. To stay under 2.0 degrees Celsius, the carbon budget is 900 gigatons of CO2, or 16 years of current emissions. 94. Causes of recent global temperature rise. Physical drivers of global warming that has happened so far. Future global warming potential for long-lived drivers like carbon dioxide emissions is not represented. Future global warming potential for long-lived drivers like carbon dioxide emissions is not represented. Whiskers on each bar show the possible error range. The climate system experiences various cycles on its own which can last for years, decades or even centuries. For example, El Niño events cause short-term spikes in surface temperature while La Niña events cause short-term cooling. 95. Their relative frequency can affect global temperature trends on a decadal timescale. 96. Other changes are caused by an imbalance of energy from external forcings. 97. Examples of these include changes in the concentrations of greenhouse gases, solar luminosity, volcanic eruptions, and variations in the Earth's orbit around the Sun. 98. To determine the human contribution to climate change, unique fingerprints for all potential causes are developed and compared with both observed patterns and known internal climate variability. 99. For example, solar forcing, whose fingerprint involves warming the entire atmosphere, is ruled out because only the lower atmosphere has warmed. 100. Atmospheric aerosols produce a smaller, cooling effect. Other drivers, such as changes in albedo, are less impactful. 101. Greenhouse gases. CO2 concentrations over the last 800,000 years as measured from ice cores, blue, green, and directly black. Greenhouse gases are transparent to sunlight, and thus allow it to pass through the atmosphere to heat the Earth's surface. The Earth radiates it as heat, and greenhouse gases absorb a portion of it. This absorption slows the rate at which heat escapes into space, trapping heat near the Earth's surface and warming it over time. 102. While water vapor approximately equals 50% and clouds approximately equals 25% are the biggest contributors to the greenhouse effect, they primarily change as a function of temperature and are therefore mostly considered to be feedbacks that change climate sensitivity. On the other hand, concentrations of gases such as CO2 approximately equals 20%, tropospheric ozone, 103 CFCs and nitrous oxide are added or removed independently from temperature, and are therefore considered to be external forcings that change global temperatures. 104. Before the Industrial Revolution, naturally occurring amounts of greenhouse gases caused the air near the surface to be about 33 degrees Celsius warmer than it would have been in their absence. 105. 106. Human activity since the Industrial Revolution, mainly extracting and burning fossil fuels coal, oil, and natural gas 107 has increased the amount of greenhouse gases in the atmosphere. In 2022, the concentrations of CO2 and methane had increased by about 50% and 164%, respectively, since 1750. 108. These CO2 levels are higher than they have been at any time during the last 14 million years. 109. Concentrations of methane are far higher than they were over the last 800,000 years. 110. The Global Carbon Project shows how additions to CO2 since 1880 have been caused by different sources ramping up one after another. Global human-caused greenhouse gas emissions in 2019 were equivalent to 59 billion tons of CO2. Of these emissions, 75% was CO2, 18% was methane, 4% was nitrous oxide, and 2% was fluorinated gases. 111. CO2 emissions primarily come from burning fossil fuels to provide energy for transport, manufacturing, heating, and electricity. 5. Additional CO2 emissions come from deforestation and industrial processes, which include the CO2 released by the chemical reactions for making cement, steel, aluminum, and fertilizer. 112. 113. 114. 115. Methane emissions come from livestock, manure, rice cultivation, landfills, wastewater, and coal mining, as well as oil and gas extraction. 116. 117. Nitrous oxide emissions largely come from the microbial decomposition of fertilizer. 118. 119. While methane only lasts in the atmosphere for an average of 12 years, 120. CO2 lasts much longer. The Earth's surface absorbs CO2 as part of the carbon cycle. While plants on land and in the ocean absorb most excess emissions of CO2 every year, that CO2 is returned to the atmosphere when biological matter is digested, burns, or decays. 121 Land surface carbon sink processes, such as carbon fixation in the soil and photosynthesis, remove about 29% of annual global CO2 emissions. 122 The ocean has absorbed 20 to 30% of emitted CO2 over the last 2 decades. 123 CO2 is only removed from the atmosphere for the long term when it is stored in the Earth's crust, which is a process that can take millions of years to complete. 121 Land surface changes. The rate of global tree cover loss has approximately doubled since 2001, to an annual loss approaching an area the size of Italy. 124 Around 30% of Earth's land area is largely unusable for humans, glaciers, deserts, etc. 26% is forests, 10% is shrubland and 34% is agricultural land. 125 Deforestation is the main land use change contributor to global warming. 126 As the destroyed trees release CO2, and are not replaced by new trees, removing that carbon sink. 127 Between 2001 and 2018, 27% of deforestation was from permanent clearing to enable agricultural expansion for crops and livestock. Another 24% has been lost to temporary clearing under the shifting cultivation agricultural systems. 26% was due to logging for wood and derived products, and wildfires have accounted for the remaining 23%. 128 Some forests have not been fully cleared, but were already degraded by these impacts. Restoring these forests also recovers their potential as a carbon sink. 129 Local vegetation cover impacts how much of the sunlight gets reflected back into space, albedo, and how much heat is lost by evaporation. For instance, the change from a dark forest to grassland makes the surface lighter, causing it to reflect more sunlight. Deforestation can also modify the release of chemical compounds that influence clouds, and by changing wind patterns. 130 In tropic and temperate areas the net effect is to produce significant warming, and forest restoration can make local temperatures cooler. 129 At latitudes closer to the poles, there is a cooling effect as forest is replaced by snow-covered and more reflective plains. 130 Globally, these increases in surface albedo have been a dominant direct influence on temperature from land use change. Thus, land use change to date is estimated to have a slight cooling effect. 131 Other factors. Aerosols and clouds. Air pollution, in the form of aerosols, affects the climate on a large scale. 132 Aerosols scatter and absorb solar radiation. From 1961 to 1990, a gradual reduction in the amount of sunlight reaching the Earth's surface was observed. This phenomenon is popularly known as global dimming. 133 and is primarily attributed to sulfate aerosols produced by the combustion of fossil fuels with heavy sulfur concentrations like coal and bunker fuel. 53 Smaller contributions come from black carbon, from combustion of fossil fuels and biomass, and from dust. 134, 135, 136 Globally, aerosols have been declining since 1990 due to pollution controls, meaning that they no longer mask greenhouse gas warming as much. 137, 53 Aerosols also have indirect effects on the Earth's energy budget. Sulfate aerosols act as cloud condensation nuclei and lead to clouds that have more and smaller cloud droplets. These clouds reflect solar radiation more efficiently than clouds with fewer and larger droplets. 138 They also reduce the growth of raindrops, which makes clouds more reflective to incoming sunlight. 139 Indirect effects of aerosols are the largest uncertainty in radiative forcing. 140 While aerosols typically limit global warming by reflecting sunlight, black carbon and soot that falls on snow or ice can contribute to global warming. Not only does this increase the absorption of sunlight, it also increases melting and sea level rise. 141 Limiting new black carbon deposits in the Arctic could reduce global warming by 0.2 degrees Celsius by 2050. 142 The effect of decreasing sulfur content of fuel oil for ships since 2020, 143, is estimated to cause an additional 0.05 degrees Celsius increase in global mean temperature by 2050. 144 Solar and volcanic activity. The Fourth National Climate Assessment NCA4, USGCRP, 2017 includes charts illustrating that neither solar nor volcanic activity can explain the observed warming. 145, 146 As the sun is the Earth's primary energy source, changes in incoming sunlight directly affect the climate system. 140 Solar irradiance has been measured directly by satellites. 147 And indirect measurements are available from the early 1600s onwards. 140 Since 1880, there has been no upward trend in the amount of the sun's energy reaching the Earth, in contrast to the warming of the lower atmosphere, the troposphere. 148 The upper atmosphere, the stratosphere, would also be warming if the sun was sending more energy to Earth, but instead, it has been cooling. 100 This is consistent with greenhouse gases preventing heat from leaving the Earth's atmosphere. 149 Explosive volcanic eruptions can release gases, dust and ash that partially block sunlight and reduce temperatures, or they can send water vapor into the atmosphere, which adds to greenhouse gases and increases temperatures. 150 These impacts on temperature only last for several years, because both water vapor and volcanic material have low persistence in the atmosphere. 151 Volcanic CO2 emissions are more persistent, but they are equivalent to less than 1% of current human-caused CO2 emissions. 152 Volcanic activity still represents the single largest natural impact forcing on temperature in the industrial era. Yet, like the other natural forcings, it has had negligible impacts on global temperature trends since the Industrial Revolution. 151 Climate change feedbacks. Sea ice reflects 50% to 70% of incoming sunlight, while the ocean, being darker, reflects only 6%. As an area of sea ice melts and exposes more ocean, more heat is absorbed by the ocean, raising temperatures that melt still more ice. This is a positive feedback process. 153 response to an initial forcing is shaped by feedbacks, which either amplify or dampen the change. Self-reinforcing or positive feedbacks increase the response, while balancing or negative feedbacks reduce it. 154 The main reinforcing feedbacks are the water vapor feedback, the ice albedo feedback, and the net effect of clouds. 155 The primary balancing mechanism is radiative cooling, as Earth's surface gives off more heat to space in response to rising temperature. 157 In addition to temperature feedbacks, there are feedbacks in the carbon cycle, such as the fertilizing effect of CO2 on plant growth. 158 Feedbacks are expected to trend in a positive direction as greenhouse gas emissions continue, raising climate sensitivity. 159 These feedback processes alter the pace of global warming. For instance, warmer air can hold more moisture in the form of water vapor, which is itself a potent greenhouse gas. 155 Warmer air can also make clouds higher and thinner, and therefore more insulating, increasing climate warming. 160 The reduction of snow cover and sea ice in the Arctic is another major feedback. This reduces the reflectivity of the Earth's surface in the region and accelerates Arctic warming. 162 This additional warming also contributes to permafrost thawing, which releases methane and CO2 into the atmosphere. 163 Around half of human-caused CO2 emissions have been absorbed by land plants and by the oceans. 164 This fraction is not static, and if future CO2 emissions decrease, the Earth will be able to absorb up to around 70%. If they increase substantially, it'll still absorb more carbon than now, but the overall fraction will decrease to below 40%. 165 This is because climate change increases droughts and heat waves that eventually inhibit plant growth on land, and soils will release more carbon from dead plants when they are warmer. 167 The rate at which oceans absorb atmospheric carbon will be lowered as they become more acidic and experience changes in thermohaline circulation and phytoplankton distribution. 168 82 Uncertainty over feedbacks, particularly cloud cover. 168 82 Uncertainty over feedbacks, particularly cloud cover. 170 is the major reason why different climate models project different magnitudes of warming for a given amount of emissions. 171 Modeling. Energy flows between space, the atmosphere, and Earth's surface. Most sunlight passes through the atmosphere to heat the Earth's surface, then greenhouse gases absorb most of the heat the Earth radiates in response. Adding to greenhouse gases increases this insulating effect, causing an energy imbalance that heats the planet up. A climate model is a representation of the physical, chemical and biological processes that affect the climate system. 172 Models include natural processes like changes in the Earth's orbit, historical changes in the sun's activity, and volcanic forcing. 173 Models are used to estimate the degree of warming future emissions will cause when accounting for the strength of climate feedbacks. 175 Models also predict the circulation of the oceans, the annual cycle of the seasons, and the flows of carbon between the land surface and the atmosphere. 176 The physical realism of models is tested by examining their ability to simulate current or past climates. 177 Past models have underestimated the rate of Arctic shrinkage. 177 Past models have underestimated the rate of Arctic shrinkage. 178 and underestimated the rate of precipitation increase. 179 Sea level rise since 1990 was underestimated in older models, but more recent models agree well with observations. 180 The 2017 United States published National Climate Assessment notes that climate models may still be underestimating or missing relevant feedback processes. 181 Additionally, climate models may be unable to adequately predict short-term regional climatic shifts. 182 A subset of climate models adds societal factors to a physical climate model. These models simulate how population, economic growth, and energy use affect and interact with the physical climate. With this information, these models can produce scenarios of future greenhouse gas emissions. This is then used as input for physical climate models and carbon cycle models to predict how atmospheric concentrations of greenhouse gases might change. 184 Depending on the socioeconomic scenario and the mitigation scenario, models produce atmospheric CO2 concentrations that range widely between 380 and 1400 ppm. 185 Impacts. The 6th IPCC assessment report projects changes in average soil moisture at 2.0 degrees Celsius of warming, as measured in standard deviations from the 1850 to 1900 baseline. Environmental effects. The environmental effects of climate change are broad and far-reaching, affecting oceans, ice, and weather. Changes may occur gradually or rapidly. Evidence for these effects comes from studying climate change in the past, from modeling, and from modern observations. 186 Since the 1950s, droughts and heat waves have appeared simultaneously with increasing frequency. 187 Extremely wet or dry events within the monsoon period have increased in India and East Asia. 188 Monsoonal precipitation over the northern hemisphere has increased since 1980. 189 The rainfall rate and intensity of hurricanes and typhoons is likely increasing. 190 And the geographic range likely expanding poleward in response to climate warming. 191 Frequency of tropical cyclones has not increased as a result of climate change. 192 Historical sea level reconstruction and projections up to 2100 published in 2017 by the U.S. Global Change Research Program. 193 Global sea level is rising as a consequence of thermal expansion and the melting of glaciers and ice sheets. Sea level rise has increased over time, reaching 4.8 centimeters per decade between 2014 and 2023. 194 Over the 21st century, the IPCC projects 32 to 62 cm of sea level rise under a low emission scenario, 44 to 76 cm under an intermediate one, and 65 to 101 cm under a very high emission scenario. 195 Marine ice sheet instability processes in Antarctica may add substantially to these values, 196 including the possibility of a 2-meter sea level rise by 2100 under high emissions. 197 Climate change has led to decades of shrinking and thinning of the Arctic sea ice. 198 While ice-free summers are expected to be rare at 1.5 degrees Celsius degrees of warming, they are set to occur once every 3 to 10 years at a warming level of 2 degrees Celsius. 199 Higher atmospheric CO2 concentrations cause more CO2 to dissolve in the oceans, which is making them more acidic. 200 Because oxygen is less soluble in warmer water. 201 Its concentrations in the ocean are decreasing, and dead zones are expanding. 202 Tipping points and long-term impacts. Different levels of global warming may cause different parts of Earth's climate system to reach tipping points that cause transitions to different states. 203 204 Greater degrees of global warming increase the risk of passing through tipping points, thresholds beyond which certain major impacts can no longer be avoided even if temperatures return to their previous state. 205 206 For instance, the Greenland ice sheet is already melting, but if global warming reaches levels between 1.7 degrees Celsius and 2.3 degrees Celsius, its melting will continue until it fully disappears. If the warming is later reduced to 1.5 degrees Celsius or less, it will still lose a lot more ice than if the warming was never allowed to reach the threshold in the first place. 207 While the ice sheets would melt over millennia, other tipping points would occur faster and give societies less time to respond. The collapse of major ocean currents like the Atlantic Meridional Overturning Circulation (AMOC) and irreversible damage to key ecosystems like the Amazon rainforest and coral reefs can unfold in a matter of decades. 204 The long-term effects of climate change on oceans include further ice melt, ocean warming, sea level rise, ocean acidification and ocean deoxygenation. 208 The timescale of long-term impacts are centuries to millennia due to CO2 feet's long atmospheric lifetime. 209 The result is an estimated total sea level rise of 2.3 meters per degree Celsius, 4.2 feet per degree Fahrenheit, after 2,000 years. 210 Oceanic CO2 uptake is slow enough that ocean acidification will also continue for hundreds to thousands of years. 211 Deep oceans below 2,000 meters, 6,600 feet, are also already committed to losing over 10% of their dissolved oxygen by the warming which occurred to date. 212 Further, the West Antarctic ice sheet appears committed to practically irreversible melting, which would increase the sea levels by at least 3.3 meters, 10 feet 10 and over approximately 2,000 years. 204 213 214 Nature and wildlife. Recent warming has driven many terrestrial and freshwater species poleward and towards higher altitudes. 215 For instance, the range of hundreds of North American birds has shifted northward at an average rate of 1.5 kilometers per year over the past 55 years. 216 Higher atmospheric CO2 levels and an extended growing season have resulted in global greening. However, heatwaves and drought have reduced ecosystem productivity in some regions. The future balance of these opposing effects is unclear. 217 A related phenomenon driven by climate change is woody plant encroachment, affecting up to 500 million hectares globally. 218 Climate change has contributed to the expansion of drier climate zones, such as the expansion of deserts in the subtropics. 219 The size and speed of global warming is making abrupt changes in ecosystems more likely. 220 Overall, it is expected that climate change will result in the extinction of many species. 221 The oceans have heated more slowly than the land, but plants and animals in the ocean have migrated towards the colder poles faster than species on land. 222 Just as on land, heat waves in the ocean occur more frequently due to climate change, harming a wide range of organisms such as corals, kelp, and seabirds. 223 Ocean acidification makes it harder for marine calcifying organisms such as mussels, barnacles and corals to produce shells and skeletons, and heat waves have bleached coral reefs. 224 Harmful algal blooms enhanced by climate change and eutrophication lower oxygen levels, disrupt food webs and cause great loss of marine life. 225 Coastal ecosystems are under particular stress. Almost half of global wetlands have disappeared due to climate change and other human impacts. 226 Plants have come under increased stress from damage by insects. 227 Climate change impacts on the environment. Ecological collapse. Coral bleaching from thermal stress has damaged the Great Barrier Reef and threatens coral reefs worldwide. 228 Extreme weather. Drought and high temperatures worsen the 2020 bushfires in Australia. 229 Arctic warming. Permafrost thaws undermine infrastructure and release methane, a greenhouse gas. 163 Habitat destruction. Many Arctic animals rely on sea ice, which has been disappearing in a warming Arctic. 230 Pest propagation. Mild winters allow more pine beetles to survive to kill large swaths of forest. 231 Humans. Extreme weather will be progressively more common as the Earth warms. 232 The effects of climate change are impacting humans everywhere in the world. 233 Impacts can be observed on all continents and ocean regions. 234 With low latitude, less developed areas facing the greatest risk. 235 Continued warming has potentially severe, pervasive and irreversible impacts for people and ecosystems. 236 The risks are unevenly distributed, but are generally greater for disadvantaged people in developing and developed countries. 237. Health and food. The World Health Organization calls climate change one of the biggest threats to global health in the 21st century. 13. Scientists have warned about the irreversible harms it poses. 238. Extreme weather events affect public health, and food and water security. 239, 240, 241. Temperature extremes lead to increased illness and death. 239, 240. Climate change increases the intensity and frequency of extreme weather events. 240, 241. It can affect transmission of infectious diseases, such as dengue fever and malaria. 238, 239. According to the World Economic Forum, 14.5 million more deaths are expected due to climate change by 2050. 242. 30% of the global population currently live in areas where extreme heat and humidity are already associated with excess deaths. 243, 244. By 2100, 50% to 75% of the global population would live in such areas. 243, 245. While total crop yields have been increasing in the past 50 years due to agricultural improvements, climate change has already decreased the rate of yield growth. 241. Fisheries have been negatively affected in multiple regions. 241. While agricultural productivity has been positively affected in some high-latitude areas, mid and low-latitude areas have been negatively affected. 241. According to the World Economic Forum, an increase in drought in certain regions could cause 3.2 million deaths from malnutrition by 2050 and stunting in children. 246. With 2 degrees Celsius warming, global livestock headcounts could decline by 7–10% by 2050, as less animal feed will be available. 247. If the emissions continue to increase for the rest of century, then over 9 million climate-related deaths would occur annually by 2100. 248. Livelihoods and inequality. Economic damages due to climate change may be severe and there is a chance of disastrous consequences. 249. Severe impacts are expected in Southeast Asia and Sub-Saharan Africa, where most of the local inhabitants are dependent upon natural and agricultural resources. 250. 251. Heat stress can prevent outdoor laborers from working. If warming reaches 4 degrees Celsius, then labor capacity in those regions could be reduced by 30 to 50%. 252. The World Bank estimates that between 2016 and 2030, climate change could drive over 120 million people into extreme poverty without adaptation. 253. Inequalities based on wealth and social status have worsened due to climate change. 254. Major difficulties in mitigating, adapting to, and recovering from climate shocks are faced by marginalized people who have less control over resources. 255. 250. Indigenous people, who are subsistent on their land and ecosystems, will face endangerment to their wellness and lifestyles due to climate change. 256. An expert elicitation concluded that the role of climate change in armed conflict has been small compared to factors such as socioeconomic inequality and state capabilities. 257. While women are not inherently more at risk from climate change and shocks, limits on women's resources and discriminatory gender norms constrain their adaptive capacity and resilience. 258. For example, women's work burdens, including hours worked in agriculture, tend to decline less than men's during climate shocks such as heat stress. 258. Climate migration. Low-lying islands and coastal communities are threatened by sea level rise, which makes urban flooding more common. Sometimes, land is permanently lost to the sea. 259. This could lead to statelessness for people in island nations, such as the Maldives and Tuvalu. 260. In some regions, the rise in temperature and humidity may be too severe for humans to adapt to. 261. With worst-case climate change, models project that almost one-third of humanity might live in Sahara-like uninhabitable and extremely hot climates. 262. These factors can drive climate or environmental migration, within and between countries. 263. More people are expected to be displaced because of sea level rise, extreme weather and conflict from increased competition over natural resources. Climate change may also increase vulnerability, leading to trapped populations, who are not able to move due to a lack of resources. 264. Climate change impacts on people. Environmental migration. Sparser rainfall leads to desertification that harms agriculture and can displace populations. Shown, Telly, Molly 2008. 265. Agricultural changes. Droughts, rising temperatures, and extreme weather negatively impact agriculture. Shown, Texas, U.S. 2013. 266. Tidal flooding. Sea level rise increases flooding in low-lying coastal regions. Shown, Venice, Italy 2004. 267. Storm intensification. Bangladesh after Cyclone Sidr 2007 is an example of catastrophic flooding from increased rainfall. 268. Heat wave intensification. Events like the 2022 Southern Cone heat wave are becoming more common. 269. Reducing and recapturing emissions. Global greenhouse gas emission scenarios, based on policies and pledges as of November 2021. Climate change can be mitigated by reducing the rate at which greenhouse gases are emitted into the atmosphere, and by increasing the rate at which carbon dioxide is removed from the atmosphere. 270. To limit global warming to less than 1.5 degrees Celsius, global greenhouse gas emissions needs to be net zero by 2050, or by 2070 with a 2 degrees Celsius target. 271. This requires far-reaching, systemic changes on an unprecedented scale in energy, land, cities, transport, buildings, and industry. 272. The United Nations Environment Programme estimates that countries need to triple their pledges under the Paris Agreement within the next decade to limit global warming to 2 degrees Celsius. An even greater level of reduction is required to meet the 1.5 degrees Celsius goal. 273. With pledges made under the Paris Agreement as of 2024, there would be a 66% chance that global warming is kept under 2.8 degrees Celsius by the end of the century, range 1.9–3.7 degrees Celsius, depending on exact implementation and technological progress. When only considering current policies, this raises to 3.1 degrees Celsius. 274. Globally, limiting warming to 2 degrees Celsius may result in higher economic benefits than economic costs. 275. Although there is no single pathway to limit global warming to 1.5 or 2 degrees Celsius, 276. Most scenarios and strategies see a major increase in the use of renewable energy in combination with increased energy efficiency measures to generate the needed greenhouse gas reductions. 277. To reduce pressures on ecosystems and enhance their carbon sequestration capabilities, changes would also be necessary in agriculture and forestry. 278. Such as preventing deforestation and restoring natural ecosystems by reforestation. 279. Other approaches to mitigating climate change have a higher level of risk. Scenarios that limit global warming to 1.5 degrees Celsius typically project the large-scale use of carbon dioxide removal methods over the 21st century. 280. There are concerns, though, about over-reliance on these technologies and environmental impacts. 281. Solar radiation modification, SRM, is also a possible supplement to deep reductions in emissions. However, SRM raises significant ethical and legal concerns, and the risks are imperfectly understood. 282. Clean energy. Coal, oil, and natural gas remain the primary global energy sources even as renewables have begun rapidly increasing. 283. Wind and solar power, Germany. Renewable energy is key to limiting climate change. 284. For decades, fossil fuels have accounted for roughly 80% of the world's energy use. 285. The remaining share has been split between nuclear power and renewables, including hydropower, bioenergy, wind and solar power and geothermal energy. 286. Fossil fuel use is expected to peak in absolute terms prior to 2030 and then to decline, with coal use experiencing the sharpest reductions. 287. Renewables represented 86% of all new electricity generation installed in 2023. 288. Other forms of clean energy, such as nuclear and hydropower, currently have a larger share of the energy supply. However, their future growth forecasts appear limited in comparison. 289. While solar panels and onshore wind are now among the cheapest forms of adding new power generation capacity in many locations, 290. Green energy policies are needed to achieve a rapid transition from fossil fuels to renewables. 291. To achieve carbon neutrality by 2050, renewable energy would become the dominant form of electricity generation, rising to 85% or more by 2050 in some scenarios. Investment in coal would be eliminated and coal use nearly phased out by 2050. 292. 293. Electricity generated from renewable sources would also need to become the main energy source for heating and transport. 294. Transport can switch away from internal combustion engine vehicles and towards electric vehicles, public transit, and active transport, cycling and walking. 295. 296. For shipping and flying, low-carbon fuels would reduce emissions. 295. Heating could be increasingly decarbonized with technologies like heat pumps. 297. There are obstacles to the continued rapid growth of clean energy, including renewables. 298. Wind and solar produce energy intermittently and with seasonal variability. Traditionally, hydro dams with reservoirs and fossil fuel power plants have been used when variable energy production is low. Going forward, battery storage can be expanded, energy demand and supply can be matched, and long-distance transmission can smooth variability of renewable outputs. 284. Bioenergy is often not carbon neutral and may have negative consequences for food security. 299. The growth of nuclear power is constrained by controversy around radioactive waste, nuclear weapon proliferation, and accidents. 300. 301. Hydropower growth is limited by the fact that the best sites have been developed, and new projects are confronting increased social and environmental concerns. 302. Low-carbon energy improves human health by minimizing climate change as well as reducing air pollution deaths, 303, which were estimated at 7 million annually in 2016. 304. Meeting the Paris Agreement goals that limit warming to a 2 degrees Celsius increase could. Low-carbon energy improves human health by minimizing climate change as well as reducing air pollution deaths, 303, which were estimated at 7 million annually in 2016. 304. Meeting the Paris Agreement goals that limit warming to a 2 degrees Celsius increase could save about 1 million of those lives per year by 2050, whereas limiting global warming to 1.5 degrees Celsius could save millions and simultaneously increase energy security and reduce poverty. 305. Improving air quality also has economic benefits which may be larger than mitigation costs. 306. Energy conservation. Reducing energy demand is another major aspect of reducing emissions. 307. If less energy is needed, there is more flexibility for clean energy development. It also makes it easier to manage the electricity grid, and minimizes carbon-intensive infrastructure development. 308. Major increases in energy efficiency investment will be required to achieve climate goals, comparable to the level of investment in renewable energy. 309. Several COVID-19-related changes in energy use patterns, energy efficiency investments, and funding have made forecasts for this decade more difficult and uncertain. 310. Strategies to reduce energy demand vary by sector. In the transport sector, passengers and freight can switch to more efficient travel modes, such as buses and trains, or use electric vehicles. 311 Industrial strategies to reduce energy demand include improving heating systems and motors, designing less energy-intensive products, and increasing product lifetimes. 312 In the building sector, the focus is on better design of new buildings, and higher levels of energy efficiency in retrofitting. 313 The use of technologies like heat pumps can also increase building energy efficiency. 314 Agriculture and industry. Taking into account direct and indirect emissions, industry is the sector with the highest share of global emissions. Data as of 2019 from the IPCC. Agriculture and forestry face a triple challenge of limiting greenhouse gas emissions, preventing the further conversion of forests to agricultural land, and meeting increases in world food demand. 315 A set of actions could reduce agriculture and forestry-based emissions by 2/3 from 2010 levels. These include reducing growth in demand for food and other agricultural products, increasing land productivity, protecting and restoring forests, and reducing greenhouse gas emissions from agricultural production. 316 On the demand side, a key component of reducing emissions is shifting people towards plant-based diets. 317 Eliminating the production of livestock for meat and dairy would eliminate about 3/4 of all emissions from agriculture and other land use. 318 Livestock also occupy 37% of ice-free land area on Earth and consume feed from the 12% of land area used for crops, driving deforestation and land degradation. 319 Steel and cement production are responsible for about 13% of industrial CO2 emissions. In these industries, carbon-intensive materials such as coke and lime play an integral role in the production, so that reducing CO2 emissions requires research into alternative chemistries. 320 Where energy production or CO2-intensive heavy industries continue to produce waste CO2, technology can sometimes be used to capture and store most of the gas instead of releasing it to the atmosphere. 321 This technology, carbon capture and storage (CCS), could have a critical but limited role in reducing emissions. 321 It is relatively expensive, 322, and has been deployed only to an extent that removes around 0.1% of annual greenhouse gas emissions. 321 Carbon dioxide removal. Most CO2 emissions have been absorbed by carbon sinks, including plant growth, soil uptake, and ocean uptake. 2020 Global Carbon Budget. Natural carbon sinks can be enhanced to sequester significantly larger amounts of CO2 beyond naturally occurring levels. 323 Reforestation and afforestation. Planting forests where there were none before are among the most mature sequestration techniques, although the latter raises food security concerns. 324 Farmers can promote sequestration of carbon in soils through practices such as use of winter cover crops, reducing the intensity and frequency of tillage, and using compost and manure as soil amendments. 325 Forest and landscape restoration yields many benefits for the climate, including greenhouse gas emission sequestration and reduction. 129 Restoration, recreation of coastal wetlands, prairie plots and seagrass meadows increases the uptake of carbon into organic matter. 327 When carbon is sequestered in soils and in organic matter such as trees, there is a risk of the carbon being re-released into the atmosphere later through changes in land use, fire, or other changes in ecosystems. 328 The use of bioenergy in conjunction with carbon capture and storage (BECCS) can result in net negative emissions as CO2 is drawn from the atmosphere. 329 It remains highly uncertain whether carbon dioxide removal techniques will be able to play a large role in limiting warming to 1.5 degrees Celsius. Policy decisions that rely on carbon dioxide removal increase the risk of global warming rising beyond international goals. 330 Adaptation. Adaptation is the process of adjustment to current or expected changes in climate and its effects. 331 5 Without additional mitigation, adaptation cannot avert the risk of severe, widespread and irreversible impacts. 332 More severe climate change requires more transformative adaptation, which can be prohibitively expensive. 333 The capacity and potential for humans to adapt is unevenly distributed across different regions and populations, and developing countries generally have less. 334 The first 2 decades of the 21st century saw an increase in adaptive capacity in most low and middle-income countries with improved access to basic sanitation and electricity, but progress is slow. Many countries have implemented adaptation policies. However, there is a considerable gap between necessary and available finance. 335 Adaptation to sea level rise consists of avoiding at-risk areas, learning to live with increased flooding, and building flood controls. If that fails, managed retreat may be needed. 336 There are economic barriers for tackling dangerous heat impact. Avoiding strenuous work or having air conditioning is not possible for everybody. 337 In agriculture, adaptation options include a switch to more sustainable diets, diversification, erosion control, and genetic improvements for increased tolerance to a changing climate. 338 Insurance allows for risk sharing, but is often difficult to get for people on lower incomes. 339 Education, migration and early warning systems can reduce climate vulnerability. 340 Planting mangroves or encouraging other coastal vegetation can buffer storms. 341 342 Ecosystems adapt to climate change, a process that can be supported by human intervention. By increasing connectivity between ecosystems, species can migrate to more favorable climate conditions. Species can also be introduced to areas acquiring a favorable climate. Protection and restoration of natural and semi-natural areas helps build resilience, making it easier for ecosystems to adapt. Many of the actions that promote adaptation in ecosystems also help humans adapt via ecosystem-based adaptation. For instance, restoration of natural fire regimes makes catastrophic fires less likely, and reduces human exposure. Giving rivers more space allows for more water storage in the natural system, reducing flood risk. Restored forest acts as a carbon sink, but planting trees in unsuitable regions can exacerbate climate impacts. 343. There are synergies but also trade-offs between adaptation and mitigation. 344. An example for synergy is increased food productivity, which has large benefits for both adaptation and mitigation. 345. An example of a trade-off is that increased use of air conditioning allows people to better cope with heat, but increases energy demand. Another trade-off example is that more compact urban development may reduce emissions from transport and construction, but may also increase the urban heat island effect, exposing people to heat-related health risks. 346. Examples of adaptation methods. Mangrove planting and other habitat conservation can reduce coastal flooding. Seawalls to protect against storm surge worsened by sea level rise. Green roofs to provide cooling in cities. Selective breeding for drought-resistant crops. Policies and politics. The Climate Change Performance Index ranks countries by greenhouse gas emissions 40% of score, renewable energy 20%, energy use 20%, and climate policy 20%. High, medium, low, very low. Countries that are most vulnerable to climate change have typically been responsible for a small share of global emissions. This raises questions about justice and fairness. 347. Limiting global warming makes it much easier to achieve the UN's Sustainable Development Goals, such as eradicating poverty and reducing inequalities. The connection is recognized in Sustainable Development Goal 13, which is to take urgent action to combat climate change and its impacts. 348. The goals on food, clean water and ecosystem protection have synergies with climate mitigation. 349. The geopolitics of climate change is complex. It has often been framed as a free rider problem, in which all countries benefit from mitigation done by other countries, but individual countries would lose from switching to a low-carbon economy themselves. Sometimes mitigation also has localized benefits though. For instance, the benefits of a coal phase-out to public health and local environments exceed the costs in almost all regions. 350. Furthermore, net importers of fossil fuels win economically from switching to clean energy, causing net exporters to face stranded assets, fossil fuels they cannot sell. 351. Policy options. A wide range of policies, regulations, and laws are being used to reduce emissions. As of 2019, carbon pricing covers about 20% of global greenhouse gas emissions. 352. Carbon can be priced with carbon taxes and emissions trading systems. 353. Direct global fossil fuel subsidies reached $319 billion in 2017, and $5.2 trillion when indirect costs such as air pollution are priced in. 354. Ending these can cause a 28% reduction in global carbon emissions and a 46% reduction in air pollution deaths. 355. Money saved on fossil subsidies could be used to support the transition to clean energy instead. 356. More direct methods to reduce greenhouse gases include vehicle efficiency standards, renewable fuel standards, and air pollution regulations on heavy industry. 357. Several countries require utilities to increase the share of renewables in power production. 358. Climate justice. Policy design through the lens of climate justice tries to address human rights issues and social inequality. According to proponents of climate justice, the costs of climate adaptation should be paid by those most responsible for climate change, while the beneficiaries of payments should be those suffering impacts. One way this can be addressed in practice is to have wealthy nations pay poorer countries to adapt. 359. Oxfam found that in 2023 the wealthiest 10% of people were responsible for 50% of global emissions, while the bottom 50% were responsible for just 8%. 360. Production of emissions is another way to look at responsibility. Under that approach, the top 21 fossil fuel companies would owe cumulative climate reparations of $5.4 trillion over the period 2025-2050. 361. To achieve a just transition, people working in the fossil fuel sector would also need other jobs, and their communities would need investments. 362. International climate agreements. Since 2000, rising CO2 emissions in China and the rest of the world have surpassed the output of the United States and Europe. 363. Per person, the United States generates CO2 at a far faster rate than other primary regions. 363. Nearly all countries in the world are parties to the 1994 United Nations Framework Convention on Climate Change, UNFCCC. 364. The goal of the UNFCCC is to prevent dangerous human interference with the climate system. 365. As stated in the convention, this requires that greenhouse gas concentrations are stabilized in the atmosphere at a level where ecosystems can adapt naturally to climate change, food production is not threatened, and economic development can be sustained. 366. The UNFCCC does not itself restrict emissions but rather provides a framework for protocols that do. Global emissions have risen since the UNFCCC was signed. 367. Its yearly conferences are the stage of global negotiations. 368. The 1997 Kyoto Protocol extended the UNFCCC and included legally binding commitments for most developed countries to limit their emissions. 369. During the negotiations, the G77, representing developing countries, pushed for a mandate requiring developed countries to take the lead in reducing their emissions. 370. Since developed countries contributed most to the accumulation of greenhouse gases in the atmosphere, per capita emissions were also still relatively low in developing countries, and developing countries would need to emit more to meet their development needs. 371. The 2009 Copenhagen Accord has been widely portrayed as disappointing because of its low goals, and was rejected by poorer nations including the G77. 372 Associated parties aim to limit the global temperature rise to below 2 degrees Celsius. 373 The Accord set the goal of sending $100 billion per year to developing countries for mitigation and adaptation by 2020, and proposed the founding of the Green Climate